Every star you can see tonight exists inside a bubble, not a metaphorical one, a real one, a boundary created by the speed of light, the age of the universe, and the expansion of space itself. Everything beyond that boundary is unreachable to us forever, not hidden, not waiting for better telescopes, gone. Right now, there are regions of space moving away from Earth faster than light itself. Physics allows this because nothing is actually traveling through space faster than light. Instead, space itself is stretching, carrying entire galaxies with it, like objects trapped on an expanding surface. The visible universe feels enormous. Approximately 2 trillion galaxies spread across distances so large the numbers stop feeling meaningful. But what we can see is not the universe itself. It is only the observable universe. The small fraction of reality light has had enough time to reach us from since the Big Bang, and the size of that bubble is stranger than it first appears. The universe is 13.8 billion years old, yet the edge of the observable universe sits roughly 46.5 billion light years away in every direction. Those numbers should not agree, but they do, because while light traveled toward us, space itself continued expanding the entire time. Then, in 1998, astronomers discovered something even more unsettling. The expansion of the universe was not slowing down under gravity the way everyone expected. It was accelerating. Every distant galaxy beyond our local group is moving farther away, faster and faster every second. And somewhere tonight, at the edge of the observable universe, light from a distant galaxy is crossing the cosmic horizon for the final time, stretching beyond detectability, leaving our universe permanently dark in that direction forever. Before we go any further, if you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. The story begins with the moment astronomers realized the universe had an edge at all. Long before galaxies formed their modern shapes, before planets cooled, before Earth existed at all, a clock had already started running. Not a mechanical clock, a cosmic one. Every direction you look into the night sky is also a direction backward through time, because light does not arrive instantly. It travels, slowly by the standards of the universe. When you see the Andromeda Galaxy, you are seeing light that began its journey more than 2 million years ago. The farther outward we look, the older the image becomes, until eventually distance and time become almost the same thing. That is what astronomers mean when they say observable universe. They are not describing the strength of our telescopes. Even a perfect telescope could not see beyond it. The limit comes from time itself. The universe has existed for approximately 13.8 billion years, which means light has only had 13.8 billion years to move through space and carry information toward us. But something strange happens when we turn that idea into distance. The observable universe is not 13.8 billion light years wide. It is vastly larger. The current radius measures approximately 46.5 billion light years in every direction. At first, the numbers seem impossible together. How can light travel farther than the age of the universe allows? But while the light moved toward us, space itself continued expanding underneath it. The destination kept drifting away during the journey. Every photon crossing the cosmos traveled through a universe that grew larger second by second, stretching the total distance far beyond the original starting point. Cosmologists call the limit of this visible region the cosmic horizon. Horizon here means a boundary beyond which information cannot reach you, not because something blocks it, but because there has not been enough time since the Big Bang for light to arrive. It is a horizon built from duration, a wall made from the finite age of the cosmos itself. Inside that horizon sits everything humanity has ever detected. Roughly 2 trillion galaxies, trillions upon trillions of stars, black holes, nebulae, dark matter, collapsing suns, drifting planets, and ancient radiation still moving through the dark. But beyond the horizon, the structure of reality becomes inaccessible. There may be more galaxies extending forever. Space may curve back into itself. The total universe may even be infinite. We do not know, and the hardest part is that we may never know. The observable universe is not a temporary limitation waiting for better technology to overcome. It is the only region of existence that light has allowed us to share in. Everything beyond it remains outside our conversation with the cosmos, separated from us not by engineering, but by time itself. At the top of Mount Wilson in California, cold night air moved quietly through the observatory dome, while glass photographic plates collected faint traces of distant galaxies. The year was 1929. Edwin Hubble stood beside the 100-inch Hooker telescope, at that time the most powerful telescope on Earth. For years, astronomers had assumed the universe existed in a stable, eternal state. Stars moved, galaxies rotated, but the universe itself was expected to remain fixed, like a stage holding the same scenery forever. The light arriving at Mount Wilson suggested something very different. Hubble studied a phenomenon called redshift, the stretching of light toward longer, redder wavelengths as an object moves away through space. The effect works similarly to sound lowering in pitch as a train recedes into the distance. In light, motion stretches the wave itself. The greater the stretching, the faster the object is moving away from you. Using measurements gathered partly from earlier work by Vesto Slipher, Hubble compared the distances of galaxies with the amount their light had shifted. The pattern was unmistakable. Nearly every galaxy outside our local group was receding from Earth. More surprising still, the farther away a galaxy appeared, the faster it moved away. A galaxy twice as distant receded roughly twice as fast. The universe was not static at all. It was expanding in every direction simultaneously. But the discovery carried a consequence far larger than Hubble initially emphasized. If galaxies are moving apart now, then earlier in time they must have been closer together. Run the process backward long enough, and the distances collapse toward an unimaginably dense beginning, where all matter and energy once occupied a vastly smaller state. Not an explosion inside space, an expansion of space itself. That distinction changed everything. The Big Bang was not debris flying outward into emptiness. Space expanded everywhere at once, carrying galaxies with it as the structure of the universe unfolded. Every cluster, every void, every future star system emerged from that expansion. Even the distance between galaxies grew because the fabric beneath them stretched over time. 2 years before Hubble published his findings, Belgian physicist and Catholic priest Georges Lemaitre had already reached a similar conclusion mathematically. In 1927, using Einstein's equations of general relativity, he proposed that the universe was expanding from what he called a primeval atom, an early compressed state containing all cosmic matter. Few paid attention at first. Einstein himself initially rejected the idea, but the telescope confirmed what mathematics had whispered first. The universe had a history, a beginning, a changing geometry, and once astronomers understood that space itself could evolve, the existence of a cosmic horizon became unavoidable. Light could only travel so far through a universe with a finite age. Beyond that distance, the darkness was not empty. It was simply still on its way to us. By the late 20th century, cosmology had settled into a cautious expectation. The universe was expanding, Yes, but gravity should have been slowing that expansion over time. Every galaxy pulled on every other galaxy. Every cluster added its own gravitational drag. Astronomers debated whether the cosmos would slow gently forever or eventually collapse back inward in a distant reversal sometimes called the Big Crunch. That assumption guided observations for decades. Then, in 1998, two separate research teams aimed their attention toward dying stars billions of light years away. One group was led by Saul Perlmutter at the Lawrence Berkeley National Laboratory. The other, called the High Z Supernova Search Team, included Brian Schmidt and Adam Rice. Both teams focused on Type 1a supernovae, a specific category of stellar explosion created when a white dwarf star accumulates too much matter and detonates with nearly identical brightness each time. That consistency mattered enormously because these explosions reach predictable luminosities. Astronomers can compare how bright they should appear against how bright they actually appear from Earth. The difference reveals distance with remarkable precision. Type 1a supernovae became cosmic measuring sticks, scattered across the depths of space like carefully placed markers. The teams expected to find evidence that distant galaxies had once moved outward faster before gravity gradually slowed the expansion. Instead, the supernovae appeared dimmer than expected, farther away. The only explanation consistent with the data was startling. Expansion had not been slowing down at all, it was accelerating. The farther outward astronomers measured, the clearer the pattern became. Space itself was expanding more rapidly over time, carrying galaxies apart faster with every passing billion years. The discovery overturned one of the deepest assumptions in physics almost overnight. In 2011, Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics for revealing this hidden behavior of the cosmos. But the most unsettling consequence arrived slowly. If expansion accelerates continuously, then sufficiently distant galaxies eventually recede from us faster than light itself. Not because they are breaking relativity, but because the fabric of space between us expands too quickly for light to overcome. A photon emitted toward Earth can spend billions of years crossing the universe, while the destination retreats even faster beneath it, and eventually the light loses. Galaxies near the edge of our observable horizon are already approaching this condition. Their radiation stretches toward longer wavelengths through a process called cosmological redshift, where expanding space lengthens the light wave itself over immense timescales. That light becomes weaker, colder, and more diffuse until it fades beyond detectability entirely. No explosion marks the moment. No visible boundary appears. The galaxy simply vanishes from the observable universe forever. What we once imagined as a steadily widening view of reality turns out to be temporary. The cosmic horizon is not holding still while we study it. It is tightening around us with extraordinary patience, slowly reducing the portion of existence we will ever be able to witness. Imagine releasing a ball upward from Earth and watching it continue accelerating away instead of slowing down. That was roughly the scale of the contradiction astronomers faced after the supernova measurements of 1998. Gravity should have resisted expansion. Matter should have acted like tension, pulling the universe inward across cosmic distances. Yet every new observation pointed the other direction. Space was not merely growing larger, the growth itself was speeding up. Something unseen was overpowering gravity. Physicists gave this unknown influence a practical name: dark energy. The term sounds dramatic, but it reflects uncertainty more than understanding. Dark energy is not dark in the ordinary sense. It does not absorb light. It does not emit radiation. No detector has ever observed it directly. Its existence is inferred entirely through its effect on the expansion of the universe. Much like wind inferred from the movement of trees, you cannot see clearly through fog, and according to current measurements, it dominates everything. Ordinary matter, the atoms making up stars, planets, oceans, air, and your own body, accounts for only about 5% of the universe's total energy content. Dark matter contributes approximately 27%. The remaining 68% appears to be dark energy, spread uniformly through space itself. But what exactly is it? The leading explanation traces back more than a century. In 1917, Albert Einstein modified his equations of general relativity by introducing something called the cosmological constant, a term representing a tiny outward pressure built into empty space. At the time, Einstein believed the universe was static, so he added the constant to counteract gravity and keep the cosmos balanced. When evidence for expansion emerged later, he reportedly regretted the decision, calling it his greatest blunder. History became strangely circular. The same mathematical term Einstein abandoned now resembles the simplest explanation for accelerated expansion. In this model, empty space contains an intrinsic energy that does not dilute as the universe expands. As more space appears, more of this energy appears with it. The result is subtle locally, but overwhelming across billions of light years. The measured density is astonishingly small, roughly 6/10 of a billionth of a joule per cubic meter, far less energy than a falling snowflake carries. Yet space contains so much volume that the cumulative effect governs the large scale behavior of the cosmos itself, and still, physicists remain deeply uncertain. Quantum theory predicts vacuum energy values vastly larger than observations allow, differing by as much as 120 orders of magnitude, one of the worst mismatches in modern science. Some researchers suspect dark energy may evolve over time. Others wonder whether gravity itself changes behavior across immense distances. No consensus exists. But whatever dark energy truly is, it determines the fate of the observable universe. It drives galaxies outward. It stretches the cosmic horizon tighter with age. And it ensures that regions already beyond our reach will drift farther into permanent silence, carried away by the quiet expansion of space itself. If you could leave the Milky Way behind and travel outward in a perfectly straight line, moving beyond every nearby cluster and filament without ever stopping, the observable universe would still continue for 46.5 billion light years before its visible boundary finally emerged around you. Not a physical edge, not a wall, simply the farthest distance from which light has had enough time to arrive since cosmic expansion began. That radius exists in every direction simultaneously. The scale becomes difficult to picture almost immediately. The total volume enclosed inside the observable universe measures roughly 4, followed by 80 zeros cubic meters. Numbers, this large, stop behaving like ordinary quantities in the human mind. They lose shape, but inside that vastness sits every galaxy humanity has ever detected, every quasar, every black hole, every drifting cloud of gas, illuminated by ancient stars. Current estimates suggest the observable universe contains approximately 2 trillion galaxies. For decades, astronomers believed the number was closer to 200 billion. Then, in 2016, astrophysicist Christopher Consolais and researchers at the University of Nottingham analyzed deep field observations and faint unresolved structures hidden in earlier surveys. The estimate increased dramatically. Most galaxies remain invisible to us even now. Within those galaxies exist approximately 1 septillion stars, a number written as 1 followed by 24 zeros. Around many of them orbit planets. Around some of those planets, chemistry may have organized itself into biology, and all of it exists inside the narrow region light has allowed us to examine. Our instruments continue reaching farther outward through time. In 2022, the James Webb Space Telescope observed Earendel, the most distant individual star ever detected. Its light began traveling toward us when the universe was less than 1 billion years old. Today, that star lies roughly 28 billion light years away because expansion stretched the distance during the light's journey. Webb also identified the galaxy Jades, GSZ 140, currently the most distant known galaxy. We see it as it existed only 290 million years after the Big Bang, during an era when the first stable galaxies were beginning to emerge from primordial darkness. But even Webb encounters a final limit. The oldest light visible anywhere in the sky is the cosmic microwave background, often shortened to CMB. This radiation formed approximately 380,000 years after the Big Bang, when the early universe cooled enough for electrons and protons to combine into neutral atoms. Before that moment, space was filled with opaque plasma, a dense, charged fog scattering light endlessly in every direction. The CMB marks the oldest electromagnetic signal we can ever receive. Beyond it, the universe becomes observationally silent. No telescope can see farther using light because no freely traveling light yet existed before that epoch. Everything beyond the cosmic horizon remains disconnected from direct observation, permanently outside the sphere where information and visibility overlap. Long before stars illuminated the universe, before galaxies gathered into clusters, before atoms even existed, the entire structure of the observable cosmos was being shaped inside a span of time so brief it almost escapes description. Everything we have discussed so far, horizons, expansion, cosmic structure, traces back to events unfolding within the universe's first second of existence. And most of that second remains deeply mysterious. The earliest moment physicists can meaningfully describe is called the Planck time. This occurred roughly 110 million trillion trillionths of a second after the Big Bang. At scales this extreme, the known laws of physics collapse into contradiction. General relativity, which explains gravity and cosmic structure, no longer agrees cleanly with quantum mechanics, which governs subatomic particles. Space and time themselves stop behaving in ways modern theory can fully describe. Beyond that point, certainty disappears. But shortly afterward, perhaps around 1/100 million trillion trillionth of a second into cosmic history, the universe appears to have entered a phase called inflation. Inflation was not an explosion outward into empty space. It was a sudden, exponential expansion of space itself, where distances between regions increased unimaginably fast, far faster than light could travel across them. During this brief interval, the universe expanded by at least 100 million trillion times in size, almost instantaneously. Physicists believe this expansion was driven by something called the inflaton field, a hypothetical energy field filling the newborn universe. As inflation unfolded, microscopic quantum fluctuations, tiny irregularities, smaller than atomic scales, stretched outward into enormous cosmic patterns. The seeds of every future galaxy and cluster were encoded into space during this period. But inflation created something else as well. It separated regions of space permanently. Areas once close enough to interact were thrown apart so rapidly that no signal could ever reconnect them again. Even light became too slow to bridge the growing distances. This is why the observable universe has a horizon at all. Inflation created regions forever outside one another's causal contact, meaning they can never exchange information no matter how much time passes. The horizon was born from expansion itself. By the time the universe reached 1 second old, inflation had ended, and the cosmos had cooled enough for elementary particles to stabilize into a dense plasma of protons, neutrons, electrons, and radiation. Temperatures still exceeded 10 billion degrees Celsius. Matter and light remained tightly coupled inside a glowing, opaque environment where photons scattered constantly through charged particles. Then the first atomic building blocks emerged. Around 3 minutes after the Big Bang, nucleosynthesis began. Nucleosynthesis means the formation of atomic nuclei from simpler particles. Hydrogen nuclei formed first, followed by helium and trace amounts of lithium. Nearly all ordinary matter in the modern universe still reflects those original proportions established during these opening minutes. Everything that exists today inherited its structure from that first fraction of a second. The galaxies surrounding us, the horizon limiting us, even the darkness beyond visibility, all emerged from processes unfolding before the first star had ever burned. A strange consequence emerges when inflation is allowed to continue beyond the boundaries of our observable universe. The same process that expanded our region of space may never have stopped completely. Instead, according to many modern inflation models, expansion continues elsewhere even now, endlessly generating new regions of space-time far beyond anything light could ever reveal to us. This idea began taking shape in 1980 when physicist Alan Guth introduced inflation as a solution to several deep cosmological puzzles. The observable universe appeared extraordinarily smooth and geometrically flat, despite regions being too distant to have ever exchanged information normally. Inflation solved this by proposing that all observable space originated from a much smaller connected region before expanding violently outward. But later refinements pushed the implications much further. Physicist André Linde developed versions of inflation where the process ends unevenly. In these models, inflation stops in some regions while continuing in others. One pocket of space exits inflation and forms a hot, expanding universe filled with matter and radiation. Nearby regions continue inflating, stretching farther outward until inflation eventually stops there too, producing another isolated cosmic region. Each becomes its own observable universe. Inside these separate regions, galaxies form independently. Time unfolds locally. Matter organizes itself according to the physical conditions present when inflation ended there. Some models even suggest certain physical constants could vary slightly between regions, altering how stars form or how strongly gravity behaves. And the scale involved becomes almost impossible to visualize. Conservative estimates suggest the total universe may be at least 100 sextillion times larger than the observable region surrounding us. Other inflationary models go further still, predicting space with no final boundary at all. Infinite expansion, infinite disconnected regions scattered beyond every horizon. But the important detail is not simply distance. It is causal separation. Cosmologists describe these regions as causally disconnected, meaning no signal, no light, no information can ever travel between them. The separation is not caused by technological limits or physical barriers. Space itself expands too rapidly for communication to bridge the growing gaps. Even if a signal moved forever at light speed, it would never arrive. The regions remain permanently isolated. That is why inflation matters so profoundly when discussing what lies beyond the observable universe. This is not speculation layered artificially onto cosmology. Inflation remains the strongest explanation for several observed features of reality itself, including the large scale distribution of galaxies and the smoothness of the cosmic microwave background. The same mechanism explaining the structure we see also predicts far larger structures we cannot see. And if the inflationary picture is correct, then our observable universe is not the universe in its entirety. It is one local region inside something vastly larger, perhaps endlessly larger, created by a process unfolding during the universe's earliest moments. The galaxies visible from Earth may therefore represent only a tiny fraction of what exists, surrounded on all sides by regions permanently unreachable, each carrying its own history through an expanding sea of spacetime. When astronomers first began cataloging galaxies systematically, many expected the universe to resemble a loose, random fog of island galaxies drifting through empty space. But as surveys expanded through the late 20th century, a deeper pattern slowly emerged from the darkness. The observable universe possessed structure on scales so enormous that even galaxies themselves became tiny components inside something much larger. Nothing was distributed randomly. Galaxies gather first into small gravitational families called groups. The Milky Way belongs to one such collection, the Local Group, containing more than 50 nearby galaxies bound together through gravity. These groups merge into clusters containing hundreds or sometimes thousands of galaxies immersed inside vast halos of dark matter and superheated gas. And the hierarchy continues upward. Galaxy clusters themselves gather into superclusters stretching across hundreds of millions of light years. Then superclusters connect through immense elongated filaments, forming a gigantic interconnected framework cosmologists now call the cosmic web. Between those filaments lie enormous voids where galaxies become extraordinarily sparse, creating a structure resembling an immense three-dimensional network suspended across space-time itself. The scale becomes difficult to process quickly. One of the largest known structures, the Hercules Corona Borealis Great Wall, extends approximately 10 billion light years across. That distance spans roughly 1/10 of the entire observable universe. It contains vast concentrations of galaxies woven together through linked regions so enormous they once challenged assumptions about how uniformly matter should distribute itself on cosmic scales. But the emptiness between structures can be equally astonishing. The Boates void, discovered in 1981, stretches roughly 330 million light years wide. Inside it, galaxies become startlingly rare. A civilization crossing that region for millions of years would encounter long stretches of darkness between isolated systems. Yet even these voids are not truly empty. Thin gas, dark matter, and traces of radiation still drift through them almost invisibly. And none of this emerged by accident. The entire cosmic web appears to trace back to microscopic quantum fluctuations generated during the universe's earliest moments. Inflation stretched those fluctuations outward across immense distances, imprinting tiny density differences into spacetime itself. Over billions of years, gravity amplified those denser regions gradually, drawing matter inward until filaments, clusters, and galaxies emerged from the original pattern encoded into the expanding universe. That continuity matters enormously, because if inflation operated uniformly beyond our observable horizon, then the same underlying physics almost certainly shaped regions we will never see as well. more filaments likely extend outward beyond visibility. More voids, more galaxy clusters woven through unseen expanses permanently disconnected from Earth by cosmic expansion. The observable universe, therefore, may not represent a complete map of reality at all. It may function more like a local sample extracted from something vastly larger, a small visible fragment of a structure continuing far beyond the boundaries imposed by light travel time. What we observe appears immense already, but statistically, cosmologically, it is probably only one tiny portion of a much greater architecture stretching silently through regions forever hidden beyond our horizon. There is a limit to how far light can carry information toward us, and that limit surrounds Earth in every direction like an ancient shell, frozen in time. Beyond it, ordinary observation fails completely. No telescope, no matter how advanced, will ever see farther using light alone. The boundary is called the cosmic microwave background, or CMB, and it represents the oldest visible signal in the universe. But the CMB is not an object, it is light itself. Before the universe reached approximately 380,000 years of age, space was filled with a dense plasma, a superheated mixture of electrons, protons, and radiation packed so tightly together that photons could not travel freely. Every attempt light made to move forward ended almost immediately in collision. The young cosmos resembled an endless glowing fog where radiation remained trapped inside matter itself. Then expansion cooled everything enough for a transformation to occur. As temperatures dropped to roughly 3000 Kelvin, electrons slowed and combined with protons to form the first stable hydrogen atoms. Without free charged particles scattering photons constantly, space suddenly became transparent. Light decoupled from matter and began moving freely through the universe for the first time. That light still surrounds you tonight. Over the next 13.8 billion years, cosmic expansion stretched those original wavelengths dramatically. What once glowed with visible intensity shifted downward into microwaves. Today, the radiation reaches Earth uniformly from every direction at a temperature of approximately 2.725 Kelvin, only slightly above absolute zero, and it fills all of space. The discovery happened unexpectedly in 1965 at Bell Laboratories in New Jersey. Radio astronomers Arno Penzias and Robert Wilson were calibrating a sensitive microwave antenna when they encountered a persistent background hiss they could not remove. They tested equipment repeatedly, searched for technical interference, and even cleaned pigeon droppings from inside the antenna structure, suspecting contamination might explain the noise. The signal remained constant. What they had detected was the leftover radiation from the early universe itself, ancient light still crossing space billions of years after its release. Later missions transformed that accidental discovery into one of the most precise maps in scientific history. Satellites such as WMAP and Planck measured the cosmic microwave background across the entire sky, revealing tiny temperature fluctuations differing by roughly 1 part in 100,000. Those minute variations marked the original density differences imprinted during inflation. Everything grew from them: galaxies, stars, planets, eventually biology. The largest structures in the observable universe trace back to those microscopic irregularities preserved inside the CMB. It functions almost like a fossil imprint from the young cosmos, recording conditions from an era before galaxies existed at all. But it also marks a final observational wall. No earlier light survives because none could travel freely before the plasma cleared. Beyond the cosmic microwave background, ordinary electromagnetic observation ends permanently. Only gravitational waves, or neutrinos, particles capable of moving through the earlier opaque universe, may someday carry indirect information from deeper inside, those opening moments where the visible universe itself first began taking shape. Physics approaches the hidden universe differently from philosophy. Philosophy asks what might exist beyond the horizon. Physics asks what almost certainly should exist if the laws already observed continue operating outside the region we can see. And according to current cosmology, the answer is surprisingly direct. Probably more of the same. The observable universe appears remarkably uniform on the largest scales. Galaxies distribute themselves through repeating large-scale structures. The cosmic microwave background remains nearly identical in every direction. Gravity behaves consistently across billions of light years. Because of this, cosmologists often apply something called the cosmological principle, the assumption that the universe beyond our horizon follows the same general physical laws operating inside it. If that assumption holds, then beyond visibility lie more galaxies, more stars, more planets, and possibly more life. But geometry sharpens the implication considerably. Measurements of the cosmic microwave background indicate the universe is flat to within roughly 4/10 of 1%. In cosmology, flat does not mean physically flat, like a sheet of paper. It refers to Euclidean geometry, where parallel lines remain parallel across enormous distances and space does not curve globally back onto itself. And flat universes tend toward two possibilities. Either the universe is truly infinite, or it extends so vastly beyond the observable region that the distinction becomes practically meaningless. If space continues infinitely, then every physically possible arrangement of matter must eventually repeat somewhere, simply because the number of ways particles can organize inside a finite volume is itself finite. This sounds impossible initially, but probability behaves differently inside infinity. Imagine shuffling a deck of cards forever. Eventually, identical arrangements recur. Given infinite opportunities, repetition becomes unavoidable. Cosmologist Max Tegmark applied similar reasoning to the observable universe itself and calculated that an exact duplicate of our entire observable region would statistically appear somewhere at a distance so enormous it defies ordinary comprehension. Roughly 1 followed by 10 raised to the power of 118 zeros meters away. The number is effectively unimaginable. Yet the mathematics remains straightforward. Infinite space combined with finite particle arrangements eventually produces repetition, and beyond exact repetitions would exist variations. Regions nearly identical to ours except for one altered event, different stars, different planetary histories, different evolutionary outcomes unfolding under the same physical laws. This is not mystical speculation or science fiction layered onto cosmology afterward. It emerges naturally from geometry, probability, and the observed flatness of spacetime itself. If the universe extends infinitely, then every arrangement matter can physically take must occur somewhere beyond the horizon. But the laws themselves almost certainly remain unchanged. Hydrogen still burns inside stars through nuclear fusion. Gravity still bends spacetime. Electromagnetism still shapes atoms and chemistry. The same constants governing our universe likely govern those unreachable regions as well. Only arrangement changes, and that may be the strangest realization hidden inside modern cosmology. Beyond the observable horizon, the universe is probably not fundamentally alien at all. It is simply more reality, extending outward indefinitely, carrying endless variations of matter and history through regions. light has never had enough time to connect back to us. Distance behaves strangely once the universe becomes large enough. On Earth, greater distance usually means greater travel time. But across cosmic scales, distance also changes the structure of space itself. Eventually, you reach a threshold where galaxies are no longer merely far away. They are receding because the universe between us and them continues expanding continuously. Cosmologists describe this region using the term Hubble volume. The name honors Edwin Hubble, whose observations first revealed cosmic expansion in the 1920s, though the modern concept developed decades after his death. The Hubble volume refers to the region surrounding us, bounded by the Hubble radius, the distance at which recession velocity caused by expansion reaches the speed of light. Today, that radius measures approximately 13.8 billion light years. But this creates immediate confusion. The observable universe extends much farther, roughly 46.5 billion light years in every direction. How can we observe regions more distant than the point where recession exceeds light speed? The answer lies in the changing scale of the universe itself. When the ancient light we observe today first left distant galaxies, those galaxies existed much closer to us than they do now. While the photons traveled through expanding space for billions of years, the universe itself continued stretching. The galaxies drifted progressively farther away during the journey. Some are now receding faster than light. And yet, we still see them because their earlier light began traveling under very different cosmic conditions. Relativity forbids objects moving through space faster than light locally, but it does not forbid space itself from expanding. Expansion carries galaxies apart without violating Einstein's equations. This means we currently observe galaxies already outside the modern Hubble radius, but their present state is unreachable. Any light those galaxies emit now will never arrive here because expansion increasingly overwhelms the ability of photons to cross the growing distance. We continue receiving ancient signals emitted long ago, while newer information remains permanently trapped beyond causal contact, and the situation grows more extreme over time. Dark energy continues accelerating expansion, steadily pushing additional galaxies beyond observational reach. The visible universe, therefore, shrinks functionally, even while physical space expands endlessly outward. More and more regions cross into permanent invisibility with every passing billion years. Far in the future, the sky changes completely. In approximately 150 billion years, every galaxy outside the local group will have disappeared beyond the horizon. Only the merged remnants of nearby gravitationally bound galaxies will remain visible. The cosmic microwave background will fade beyond detectability. Expansion itself may become impossible to measure observationally. Future civilizations, if any survive, could inherit a profoundly misleading cosmos. They may see only a small, isolated collection of galaxies suspended in darkness, with no evidence the larger universe ever existed. No distant clusters, no observable expansion, no detectable beginning. The evidence available to modern cosmology exists only because humanity emerged during a temporary era when the universe still reveals its history openly across the sky. At this very moment, while Earth turns quietly beneath its atmosphere, distant galaxies are slipping beyond the edge of possible contact forever. Nothing dramatic marks the event. No flash appears across the sky. No boundary becomes visible. The process unfolds silently through expansion itself, one ancient stream of photons at a time. A galaxy crossing the cosmic horizon does not vanish physically. It vanishes observationally. The light it emits toward us becomes stretched continuously as space expands between its source and Earth. Cosmologists call this redshift, the gradual lengthening of light waves toward lower energy wavelengths. As the expansion accelerates, the stretching becomes increasingly severe. Visible light shifts into infrared. Infrared drifts into microwaves. Microwaves lengthen further into radio wavelengths too weak and diffuse to detect. The galaxy fades slowly into invisibility. Eventually, the final photons arrive so stretched by expansion that their energy approaches effectively zero. No meaningful information remains encoded inside them. At that point, the galaxy has crossed permanently beyond observational reach. Its future history becomes inaccessible forever, and many galaxies already stand close to that threshold tonight. Some of the most distant galaxies observed by instruments like the James Webb Space Telescope appear as they existed less than 500 million years after the Big Bang. We observe them not as they are now, but as they existed billions of years ago when their light first began crossing the universe toward us. Today, those galaxies are unimaginably farther away. Many now reside more than 46 billion light years from Earth because cosmic expansion continued throughout the entire journey of their light. Their current appearance remains completely unknown. During the 13 billion years, their ancient photons traveled toward the Milky Way. Entire histories unfolded inside those distant systems unseen. Stars were born there. Stars died there. Galaxies may have collided and merged repeatedly while their older light still crossed intergalactic space toward us. Supermassive black holes may have grown at their centers. Some systems could already be gravitationally disrupted by accelerating expansion itself. Others may have evolved into enormous mature galaxies, bearing little resemblance to the faint, primitive structures astronomers currently observe. But none of those later events can reach us anymore. We remain connected only to their distant past. This creates a subtle but profound realization about the observable universe. What we call the visible cosmos is not a simultaneous snapshot of reality. It is a layered archive of different eras arriving together from different distances. Nearby stars appear almost current. Distant galaxies appear ancient. The farther outward we look, the farther backward through time we travel observationally. And the archive is shrinking continuously. Every year, more galaxies cross beyond recoverable contact as expansion accelerates under dark energy. The observable universe contracts slowly in practical terms, not because galaxies disappear physically, but because fewer remain capable of exchanging light with us across expanding spacetime. The sky still appears full tonight, but without announcement, without motion visible to human eyes, the universe is already becoming lonelier than it was yesterday. Not every galaxy is destined to vanish beyond the horizon. Amid the accelerating expansion of the universe, a small collection of nearby systems remains tied together strongly enough to resist being carried apart. Gravity still dominates here locally, even while dark energy stretches the larger cosmos outward in every direction. This region is called the local group. It contains the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and more than 50 smaller dwarf galaxies orbiting through shared gravitational space. Across distances of a few million light years, gravity remains powerful enough to overcome cosmic expansion completely. These galaxies are not drifting away from one another. In fact, some are moving closer. Andromeda is already approaching us now. Measurements show it traveling toward the Milky Way at roughly 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will begin colliding. But collision between galaxies rarely resembles destruction in the ordinary sense. Individual stars are separated by such enormous distances that direct stellar impacts remain unlikely. Instead, gravity reshapes everything slowly. The spiral structures of both galaxies will distort and unravel through repeated close passes. Vast streams of stars will arc outward across intergalactic space. Gas clouds will compress, triggering waves of star formation lasting hundreds of millions of years. Eventually, the two systems will merge into a single enormous elliptical galaxy, sometimes informally called Milkomeda. And long after other galaxies vanish, it will remain. The local group will continue orbiting together, while expansion carries more distant structures permanently beyond visibility. Clusters outside our gravitational neighborhood will fade away first, then superclusters, then isolated galaxies, one by one, until the observable universe contracts into a much smaller, visible domain centered entirely around the merged remnants of nearby systems. By approximately 100 billion years from now, nearly every galaxy currently visible beyond the local group will have disappeared from view completely. Darkness will dominate the sky. Only the stars belonging to the merged local group will remain observable, surrounded by an expanding emptiness where no external galaxies can any longer be detected. Future observers may never realize a larger universe once existed beyond their isolated galactic environment, but even those remaining stars are temporary. Roughly 1 trillion years into the future, star formation will largely cease as interstellar gas becomes exhausted. The brightest stars will already have died long before then, leaving behind white dwarfs, neutron stars, and black holes slowly cooling through cosmic time. The universe will enter a quieter era where little new structure forms at all. Yet, through all of it, the local group endures as a gravitational refuge. Everything beyond it is already receding toward permanent separation, carried outward by expansion faster than light can reconnect. But nearby galaxies remain bound together, resisting the larger flow of spacetime itself. In a universe increasingly defined by isolation, the local group becomes something strangely intimate, a final archipelago of stars, drifting together through an ocean that grows emptier with every passing age. For most of human history, every discovery about the universe arrived through light. Telescopes collected visible stars, radio waves, infrared radiation, and X rays, all different forms of the same electromagnetic messenger traveling across space. But light has limits. It cannot cross the opaque plasma of the early universe before the cosmic microwave background formed. Something else can. Gravitational waves move through matter almost undisturbed, carrying information from regions light itself can never reveal. These waves are not particles or radiation in the ordinary sense. They are ripples in space-time itself, generated whenever massive objects accelerate violently through the cosmos. Albert Einstein predicted their existence in 1916. According to general relativity, space and time behave like a flexible fabric responding dynamically to mass and energy. When enormous bodies move suddenly, such as black holes orbiting one another, they disturb spacetime itself. Those disturbances propagate outward at light speed as gravitational waves, stretching and compressing space extremely subtly as they pass. For decades, physicists doubted they would ever be measured directly. The distortions were unimaginably small. Detecting them required instruments sensitive enough to measure changes thousands of times smaller than a proton. Yet, on September 14th, 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, finally succeeded. The signal came from two merging black holes. They collided roughly 1.3 billion light years away, releasing more energy in a fraction of a second than all the stars in the observable universe combined emit during the same instant. By the time the waves reached Earth, they altered the length of LIGO's detectors by less than the width of an atomic nucleus. Humanity had detected space-time moving, but gravitational waves matter for another reason entirely. Unlike light, they passed freely through the dense plasma of the early universe. In principle, waves generated during the first fraction of a second after the Big Bang may still be crossing space today. Physicists call these primordial gravitational waves, ancient distortions potentially carrying direct information from epochs preceding the cosmic microwave background itself. If detected, they would transform cosmology completely. They could reveal conditions from the era of inflation, when spacetime expanded exponentially during the universe's earliest moments. Instead of observing only the afterglow released 380,000 years after the Big Bang, we could study processes occurring vastly earlier, approaching the opening fractions of cosmic history directly. Future observatories may make this possible. The European Space Agency plans to launch LISA, the Laser Interferometer Space Antenna, during the 1930s. Unlike LIGO, which operates on Earth, LISA will place detectors millions of kilometers apart in space itself, allowing sensitivity to far older and lower frequency gravitational signals. Neutrinos may offer another path. Neutrinos are nearly massless particles, interacting so weakly with matter that trillions pass through your body every second unnoticed. They also traveled freely through the early universe, long before light escaped. Future neutrino astronomy may therefore uncover indirect traces from epochs hidden permanently from ordinary observation. We may never see beyond the cosmic horizon directly, but space-time itself still carries faint echoes from those inaccessible beginnings, drifting silently through the universe even now. The word multiverse often drifts through popular culture, detached from scientific meaning, used loosely to describe alternate realities, parallel dimensions, or fictional worlds branching endlessly outward. But within physics, the term carries more precise definitions. Different multiverse models emerge from different mathematical frameworks, each rooted in existing theories rather than pure imagination, and some require surprisingly little speculation. The simplest version is called the Level 1 multiverse, proposed most clearly by cosmologist Max Tegmark. This idea does not introduce new dimensions or exotic laws of nature. It simply follows from the possibility that space extends beyond our observable horizon indefinitely. If the universe continues infinitely, then regions forever hidden from us still exist physically, obeying the same constants and the same laws governing our own observable cosmos. In that sense, the hidden universe already functions as a kind of multiverse. The Level 2 multiverse emerges from eternal inflation. In this framework, inflation ends unevenly across space-time, producing disconnected cosmic bubbles separated permanently by expansion. Each bubble forms its own observable universe. Some versions of the theory suggest different bubbles may possess slightly different physical constants, altering how stars form, how strongly gravity behaves, or how quickly cosmic expansion proceeds. And the separation between bubbles is absolute. No signal crosses between them. No observer can travel from one to another because inflation continuously expands the intervening space too rapidly for communication to bridge the gap. These universes remain causally disconnected forever. Then physics becomes stranger still. The Level 3 multiverse originates from quantum mechanics, specifically the many worlds interpretation developed by physicist Hugh Everett in the 1950s. According to this idea, quantum events do not collapse into single outcomes. Instead, every possible outcome occurs, each inside its own branching version of reality. Every measurement produces parallel histories, evolving independently afterward. The mathematics permits it. Whether nature actually behaves that way remains unknown. The most abstract proposal is the level 4 multiverse, where every mathematically consistent structure exists physically somewhere. In this picture, mathematics itself becomes reality's foundation. Any internally consistent universe capable of existing mathematically exists physically as well. This is the furthest edge of theoretical cosmology. But what matters most is that these ideas did not emerge randomly from philosophy alone. The level 1 multiverse follows naturally from infinite space. The level 2 multiverse arises directly from inflationary cosmology, currently the strongest explanation for the observable universe's large-scale structure. Even the many worlds interpretation emerges from efforts to understand quantum equations already verified experimentally countless times. None of these models are confirmed, and some may never become directly testable at all. But they are not arbitrary fantasies disconnected from science. They represent attempts to follow existing physical theories toward their logical conclusions, even when those conclusions become deeply counterintuitive. The observable universe may therefore be far less complete than it appears. What we call reality could be one local region inside something vastly larger, structured in ways human intuition was never evolved to picture clearly. A single visible chamber inside a cosmic architecture whose total scale remains permanently beyond measurement, beyond travel, and perhaps beyond comprehension itself. There is something unsettling hidden inside the laws of physics themselves, not in black holes or distant galaxies, but in the numerical values governing how reality operates everywhere in the universe. Certain constants appear balanced with extraordinary precision, calibrated so narrowly that even slight changes would produce a cosmos incapable of forming stars, planets, chemistry, or observers at all. And physicists do not know why. The strength of gravity, for example, sits within a remarkably narrow life-permitting range. If gravity were modestly stronger, stars would burn hotter and faster, collapsing too quickly for stable planetary systems to persist. If weaker, matter might never condense efficiently enough to ignite stars at all. The electron's mass matters too. Change it significantly, and atomic chemistry breaks apart. Molecules become unstable. Complex structures stop forming. Even the balance between protons and neutrons inside atomic nuclei depends delicately on several underlying constants remaining within extremely precise ranges. But the most astonishing example involves dark energy. The cosmological constant, the quantity associated with the universe's accelerating expansion, appears fine-tuned to approximately 1 part in 10, raised to the power of 120. This is the most extreme fine-tuning problem currently known in physics. If dark energy were slightly stronger, expansion would have accelerated so rapidly that galaxies could never form. Matter would separate too quickly for gravity to gather stars together. If weaker, the universe evolves differently again, and the same pattern appears repeatedly throughout fundamental physics. The constants governing electromagnetism, nuclear fusion, and particle interactions all seem balanced in ways allowing complexity to emerge over billions of years. Not optimized for humanity specifically, but permissive enough for stable structure, chemistry, and eventually life. This creates the fine-tuning problem. Why do the constants possess exactly the values required for a complex universe to exist at all? One proposed answer emerges naturally from inflationary cosmology. If inflation produced vast numbers of disconnected regions beyond our observable horizon, then different regions may possess different physical constants. Some universes expand too quickly, others collapse rapidly, some never form stars, most remain sterile forever, but a few work, and observers inevitably find themselves inside those rare regions because only such regions permit observers to evolve in the first place. This reasoning is called the anthropic principle. It does not claim the universe was designed intentionally for life. Instead, it argues that conscious beings can only appear in universes already compatible with consciousness. We observe this universe because this universe allows observation. Many physicists remain deeply uncomfortable with the idea. It can feel less like an explanation and more like surrender, replacing a deeper mechanism with statistical inevitability across an enormous cosmic landscape. Yet inflationary theory naturally predicts exactly the kind of vast multiversal structure where anthropic selection could operate. And importantly, the argument avoids requiring design or purpose imposed externally onto physics itself. The hidden universe beyond our horizon may therefore matter not only because it exists, but because it could explain why our local region possesses laws delicate enough for stars to burn slowly, planets to cool gradually, and minds like ours to emerge inside the darkness long enough to notice the balance at all. The observable universe may appear boundless when you look into the night sky, yet cosmology treats its shape as a measurable property rather than a philosophical abstraction. Space itself can possess geometry. It can curve, wrap, stretch, or extend infinitely outward depending on the conditions established during the universe's earliest moments. And remarkably, we can test some of those possibilities. Modern cosmology considers three primary large scale geometries for the universe. The first is positive curvature, where space bends back onto itself like the surface of a sphere. In such a universe, parallel paths eventually converge. The second is negative curvature, resembling a saddle shape where space spreads outward faster than ordinary Euclidean geometry predicts. The third possibility is flat geometry. Flat does not mean physically flat, like paper. It means the large scale structure of space follows ordinary Euclidean rules. Parallel lines remain parallel. Triangles add to 180 degrees. Distances behave the way basic geometry expects across enormous scales. Current observations strongly support this third option. Data from the Planck satellite, released in 2018, measured the universe as flat to within roughly 4/10 of 1%. That result carries enormous implications because a flat universe may extend infinitely, but flatness alone does not guarantee infinity. Space can still wrap around itself. Mathematicians describe this using topology, the study of how space connects globally. A universe may possess flat local geometry while remaining finite overall if space-time loops back on itself in higher dimensions. One proposed example is a three-dimensional torus, similar conceptually to a video game world where traveling far enough in one direction eventually returns you to your starting point. In such a universe, light itself could wrap around space repeatedly, and that creates a testable prediction. If the observable universe were smaller than the full wrapped geometry, astronomers might detect repeating patterns inside the cosmic microwave background, identical regions appearing in multiple directions because light completed enormous loops through space before reaching Earth. So far, no such repeating patterns have appeared. Searches through cosmic microwave background data have found no convincing evidence that space wraps around itself on scales smaller than the observable universe. This places a lower limit on cosmic size. Whatever the universe's full geometry may be, it must extend at least beyond our observable horizon and almost certainly much farther, possibly vastly farther. Some inflationary models suggest the full universe could be at least 250 times larger than the observable region surrounding us. Others imply true infinity, endless flat space continuing forever beyond every horizon. But observation reaches a permanent limit here. No matter how advanced cosmology becomes, every measurement remains trapped inside the observable universe itself. We cannot step outside spacetime to inspect its overall structure directly. We infer geometry from the local region available to us and extend those conclusions outward cautiously. The shape of the universe, therefore, remains partially hidden from us, not because the mathematics fails, but because light itself imposes boundaries on what any observer inside the cosmos can ultimately know. Across the observable universe, stars ignite in numbers so large language begins to lose scale. Around many of those stars, planets circle silently through darkness. Some are frozen, some are scorched, but a fraction appear to orbit within narrow regions where liquid water could exist across immense stretches of time. And from that realization, another question emerges naturally. Where is everyone? In 1950, physicist Enrico Fermi reportedly asked a simple version of that question during lunch with colleagues at Los Alamos. The universe appeared old enough and large enough for intelligent civilizations to arise many times over, yet Earth showed no evidence of contact, visitation, or detectable engineering on cosmic scales. That contradiction became known as the Fermi paradox. The paradox grows heavier as astronomy advances. Current estimates suggest the observable universe contains roughly 1 septillion stars. Around many of them orbit rocky worlds similar in size to Earth. The Milky Way alone may contain billions of potentially habitable planets, and our galaxy is only one among trillions. Time deepens the mystery further. The universe is approximately 13 billion and 800 million years old. Our own species developed radio technology only recently in cosmic terms, within the last century. But another civilization could have emerged millions of years earlier than humanity and spread across entire star systems long before Earth formed its first forests. Yet, the sky remains silent. But silence may not mean emptiness. Part of the paradox comes from assuming intelligent life should naturally become visible across cosmic distances. Physics complicates that assumption. Signals weaken. Civilizations may not survive long. Expansion isolates galaxies from one another over time. Even inside our observable universe, communication across intergalactic distances becomes increasingly impractical as space itself stretches continuously. Beyond the cosmic horizon, the problem becomes absolute. A civilization existing outside our observable region could possess technology beyond anything humanity can imagine, yet remain permanently inaccessible to us. No message from them can ever arrive here. No telescope can ever observe them directly. Their stars may shine brightly in their own skies, while remaining forever absent from ours. Not hidden by choice, hidden by geometry. Meanwhile, the search within our own horizon has barely begun. The SETI Institute, founded in 1984, has examined only a tiny fraction of nearby candidate stars for artificial radio signals. The search area, compared to the full galaxy, remains almost unimaginably small. New instruments continue widening that search slowly. The James Webb Space Telescope can now analyze light passing through exoplanet atmospheres, searching for biosignatures, combinations of oxygen, methane, carbon dioxide, and water vapor that may suggest biological activity. So far, no confirmed evidence of life beyond Earth has appeared, but the observable universe contains too many worlds for absence to feel simple anymore. The deeper we study the cosmos, the more the question changes from whether life exists elsewhere to whether the structure of space-time itself prevents most civilizations from ever knowing one another existed at all. Most of the universe is invisible even before we reach the cosmic horizon. The stars above you, the galaxies spread across deep space, the glowing gas clouds photographed by telescopes, all of it represents only a small fraction of what actually exists. The rest hides gravitationally. Astronomers call it dark matter, a form of matter that does not emit light, absorb light, or reflect light in any detectable way. We cannot photograph it directly because electromagnetic radiation passes through it almost untouched. But gravity reveals its presence constantly through the motion of visible objects. Galaxies behave as though something enormous surrounds them. The first strong evidence appeared in 1933 when Swiss astronomer Fritz Zwicky studied the Coma cluster, a massive collection of galaxies roughly 300 million light-years away. The galaxies inside the cluster moved far too quickly for the visible matter present. According to Newtonian gravity, the cluster should have flown apart long ago, but it remained intact. Zwicky concluded, unseen mass must dominate the cluster gravitationally. At the time, many astronomers remained skeptical. The evidence felt indirect, almost unsettlingly incomplete. But decades later, Vera Rubin uncovered the same problem inside individual galaxies themselves. During the 1970s, Rubin measured how quickly stars orbited around galactic centers. According to ordinary gravity, stars farther from the center should move more slowly, much as outer planets in the solar system orbit more gradually than inner ones. But galaxies refuse to behave that way. Stars near galactic edges orbited almost as quickly as stars much closer inward. The visible mass alone could not generate enough gravity to hold those systems together. Something unseen surrounded every galaxy in an enormous halo extending far beyond the luminous stars themselves. Without that hidden mass, galaxies would unravel. Today, cosmological measurements suggest ordinary matter, everything made from atoms, planets, oceans, stars, and living organisms, accounts for only about 5% of the universe's total energy content. Dark matter contributes roughly 27%. Dark energy dominates the remainder. And yet, dark matter's true nature remains unknown. Physicists have proposed many candidates. WIMPs, short for weakly interacting massive particles, represent one major possibility. Axions, hypothetical ultralight particles emerging from quantum theory, remain another. Some researchers even consider primordial black holes formed during the earliest moments after the Big Bang. So far, none have been confirmed. But dark matter's gravitational influence shapes the universe everywhere we look. The vast filaments of the cosmic web trace its distribution. Long before galaxies formed, invisible dark matter gathered first, creating dense gravitational scaffolding that ordinary gas later flowed into. The visible universe therefore grew around an invisible skeleton, and beyond our horizon, that hidden architecture almost certainly continues. The galaxies we cannot see may still cluster along immense dark matter filaments stretching across regions forever unreachable from Earth. Entire structures, larger than anything inside our observable universe, may already exist out there silently. Governed by matter, humanity still cannot identify, despite depending on its gravity, to explain nearly every large scale structure we observe in the cosmos. If you could drift far enough away from the crowded filaments of galaxies, beyond the glowing clusters and luminous spirals, you would eventually enter regions where the universe becomes strangely sparse. Not dark in the ordinary sense, but thin, diluted, vast stretches where galaxies almost disappear entirely. Astronomers call these regions cosmic voids. The largest known example near our own region of space is the Boötes Void, discovered in 1981 by astronomers Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman. It spans roughly 330 million light years across. Within a region that enormous, astronomers expected to find thousands of galaxies. Instead, they found only around 60, and even those are scattered thinly. At first glance, voids appear almost impossible. Gravity naturally pulls matter together over time, building galaxies, clusters, and the enormous filaments threading across the observable universe. Yet gravity also creates emptiness indirectly. As matter gathers into denser structures, surrounding regions lose material, becoming progressively emptier across billions of years. The universe separates itself unevenly, but voids are not truly empty. Dark matter still drifts through them. Thin traces of hydrogen gas remain suspended there. A few isolated galaxies survive inside these enormous expanses, orbiting through near solitude. Dark energy fills them completely as well, because dark energy permeates all of spacetime uniformly, regardless of how much matter exists nearby. Still, voids remain the closest thing nature produces to genuine nothingness, and remarkably, they dominate the cosmos by volume. Roughly 80% of the observable universe consists of these low density regions rather than the bright galactic filaments visible in astronomical imagery. Most of existence is not crowded with stars. Most of existence is separation, silence between structures. Beyond our observable horizon, even larger voids may exist. Inflationary cosmology predicts that quantum fluctuations during the universe's earliest moments seeded structure unevenly across incomprehensible scales. Some distant regions may therefore contain almost no galaxies at all across billions of light years. Entire expanses nearly empty forever. But emptiness itself evolves. As dark energy continues accelerating cosmic expansion, galaxies gradually recede from one another more rapidly. Clusters become isolated, filaments thin. Over unimaginable stretches of time, the large-scale structure of the universe slowly dissolves into increasing separation. The bright architecture visible today becomes fragmented and distant. The future cosmos begins resembling a void. Not because matter disappears entirely, but because space expands faster than gravitational structures can remain connected across large distances. The universe grows quieter structurally, less dense, less interconnected, and this changes how we think about nothingness itself. A void is not the absence of existence. Physical laws still operate there. Dark matter still exerts gravity. Quantum fields still fluctuate invisibly through space-time. Expansion continues. Time continues. Even emptiness possesses structure and energy. The silence inside a cosmic void, therefore, is not truly emptiness at all. It is another arrangement of the same universe, one where matter has become so sparse across such enormous scales that space itself begins to feel like the dominant feature of reality. Far in the future, long after humanity and Earth are gone, the night sky will continue changing in ways no living observer today will ever witness directly. Not through explosions or sudden collapse, but through disappearance so gradual it unfolds across trillions of years, one galaxy at a time. Every distant galaxy currently visible beyond the local group is receding through expanding space. As those galaxies move farther away, the light they emit stretches continuously. Wavelengths lengthen, energy decreases. Visible light becomes infrared, then microwave, then radio waves extending across distances larger than planets, larger than solar systems. Eventually, the light becomes undetectable entirely. This process is called cosmological redshift, and it transforms the observable universe slowly but permanently. The last photons arriving from distant galaxies do not vanish abruptly. They thin outward into wavelengths so enormous that no conceivable detector could meaningfully capture them anymore. The universe fades structurally. In roughly 2 trillion years, even the cosmic microwave background will disappear from practical observation. The ancient radiation left from the early universe, currently measurable at 2.725 degrees above absolute zero, will have stretched into wavelengths larger than galactic scales themselves. At that point, the evidence for cosmic expansion vanishes from the sky. An observer living during that era would see something profoundly different from the universe visible tonight. By then, the Milky Way and Andromeda will already have merged into a single giant elliptical galaxy, often called Milkomeda. Most nearby dwarf galaxies will have merged with it as well through repeated gravitational interactions. Beyond that local cluster, darkness. Not empty darkness, but unreachable darkness. Other galaxies will still exist physically beyond the cosmic horizon, yet no light from them will ever arrive again. Expansion will have carried them permanently beyond observational contact. Imagine standing beneath such a sky. No distant galaxies scattered across space. No measurable redshift. No cosmic microwave background glowing faintly across every direction. Future astronomers inside Milkomeda may conclude they inhabit an eternal, static island universe surrounded by emptiness. And based on the evidence available to them, that conclusion would appear perfectly reasonable. They would possess no observational path leading toward the Big Bang, no indication that billions of galaxies once filled the visible cosmos, no direct evidence that space-time itself expands. The great discoveries of 20th and 21st century cosmology would become almost impossible to rediscover independently. But none of the missing structures would actually be gone completely. Their ancient photons would simply no longer reach the observers searching for them. This changes how we think about our own place in cosmic history. The evidence allowing us to reconstruct the universe's origin exists only during a relatively narrow window of time. We happen to live early enough for the sky to remain transparent to its own history. That timing is extraordinary. Right now, tonight, the universe still carries readable traces of its beginning across space itself. Galaxies still shine from enormous distances. Ancient radiation still surrounds us faintly. Expansion remains measurable, and one day, all of it will quietly pass beyond sight forever. Imagine drifting outward for billions of years, leaving behind every familiar galaxy, one by one. The Milky Way fades first, then the local group disappears into distance. Eventually, even the farthest galaxies visible from Earth shrink into ancient points of light behind you. And then, at last, you reach the cosmic horizon. Except nothing happens. No boundary appears in space. No glowing edge, no invisible membrane stretched across the universe. There is no physical marker separating the observable universe from whatever lies beyond it, because the horizon is not an object located somewhere in space. It is a relationship between space, time, and light. The observable horizon exists only relative to the observer measuring it. For us on Earth, it marks the maximum distance light has traveled since the Big Bang. But if you moved far enough away, your horizon would move with you automatically. The universe would recenter itself around your new position. From that location, you would possess an entirely different observable universe, extending roughly 46 billion and 500 million light years outward in every direction. Regions permanently hidden from Earth would become visible to you for the first time. New galaxies would emerge across the sky. Clusters humanity will never observe could drift into view. Entire structures beyond our current cosmic horizon might become visible from your position because their light would finally have enough time to reach you there. But the exchange works both ways. As your observable universe shifted, some regions formerly visible from Earth would vanish behind your own horizon instead. The Milky Way itself might eventually disappear from your sky. Earth would recede beyond observational reach, just as distant galaxies recede beyond ours today. From your perspective, we would become hidden. This creates one of the strangest consequences of modern cosmology. Every observer anywhere in the universe carries a unique, observable universe centered entirely around themselves. No observer occupies a privileged location. Horizons move continuously with the vantage point measuring them. The cosmos has no universal center. And if space extends infinitely, as many cosmological models suggest, then infinitely many observable universes may exist simultaneously, each overlapping partially with others while remaining incomplete individually. Some galaxies visible from Earth are invisible elsewhere. Some regions visible elsewhere remain permanently inaccessible to us. Reality depends partly on position. But importantly, crossing the horizon changes nothing locally. The laws of physics remain identical. Atoms behave the same way. Gravity operates normally. Space itself does not announce that you entered a previously unobservable region. The horizon is informational, not physical. It defines what signals can reach you, not where matter can exist. This means the hidden universe beyond our horizon is not fundamentally different from the observable universe surrounding us now. It is simply unreachable from our present location in spacetime. Somewhere beyond the darkness we cannot see, observers may look outward from their own galaxies and conclude their observable universe is complete. And from their perspective, it is we who lie beyond the edge, permanently hidden behind a horizon they can never cross either. Long after the final galaxies disappear beyond one another's horizons, after the last stars exhaust their fuel and the night sky grows permanently dark, the universe continues evolving. Expansion does not stop. Time does not stop. Even emptiness changes slowly across unimaginable spans of duration. And according to modern cosmology, all of it moves toward the same ending. Physicists call this fate the heat death of the universe. Despite the dramatic name, it is not an explosion or collapse. It is a state of maximum entropy, meaning energy becomes distributed so evenly throughout space-time that no useful work can occur anymore. No gradients remain. Stars exist because energy flows unevenly from hot regions toward colder surroundings. Life depends on similar imbalance. Galaxies form because gravity gathers matter into dense structures separated from emptier space. Every process in nature relies on differences, concentrations, motion, temperature, and structure. Heat death removes those differences gradually. Over trillions upon trillions of years, stars burn out one by one. White dwarfs cool into dark remnants. Neutron stars decay slowly. Galaxies lose their organized structure through gravitational interactions and expansion. Matter itself may eventually become unstable over sufficiently enormous timescales, though proton decay remains unconfirmed experimentally. But black holes persist longest. These objects, once thought eternal, slowly evaporate through a quantum process proposed by Stephen Hawking in 1974. Hawking radiation allows black holes to lose energy gradually by emitting faint thermal particles near their event horizons. The larger the black hole, the slower the process. Supermassive black holes containing billions of solar masses require approximately 10 raised to the power of 100 years to evaporate completely. That number is so vast it dwarfs every previous timescale discussed in cosmology combined. Yet eventually, even they disappear. After the last black holes evaporate, the universe enters its final known phase. Space contains only thin radiation, low energy photons, neutrinos, electrons, and sparse particles drifting farther apart forever through expanding spacetime. Temperature approaches absolute zero. Not perfectly zero, because quantum fields still fluctuate faintly, but so close that meaningful thermal processes effectively cease everywhere. No stars remain to produce light. No galaxies remain to organize matter. No chemistry unfolds. Complexity fades permanently from the cosmos. And this fate applies not only to our observable universe. Whatever exists beyond the cosmic horizon follows the same thermodynamic laws. Hidden galaxies, unreachable civilizations, infinite regions of unseen space, all remain governed by entropy if the laws of physics remain consistent across the larger universe. And current evidence strongly suggests they do. The hidden universe, therefore, does not escape time. No matter how vast reality may be beyond our horizon, expansion continues there too. Stars die there too. Entropy rises there too. Even infinite space does not prevent thermodynamic equilibrium from eventually dominating locally across cosmic history. The final state of the universe is therefore not violent destruction but dilution. Structure thins slowly into stillness. Energy spreads endlessly across expanding darkness. And in the farthest future imaginable, the observable universe and the hidden universe alike dissolve into the same silent equilibrium, where space-time itself continues outward, almost empty forever. Across the observable universe, the laws of physics appear remarkably stable. Gravity behaves the same in distant galaxies as it does here. Electrons carry the same charge everywhere we measure them. Light travels at the same speed through the vacuum of space in every direction we observe. But stability alone is not the strange part. The deeper mystery is how narrowly balanced these values appear to be. Tiny changes to certain physical constants would produce a universe so different that stars, chemistry, planets, and biology could never emerge at all. The cosmological constant is one example. This quantity describes the energy density of empty space itself, the same phenomenon now associated with dark energy. Observations suggest its value is extraordinarily small, but not zero. If it had been only modestly larger in the early universe, expansion would have accelerated too rapidly for matter to gather into galaxies. No galaxies, no stars. Without stars, heavier elements such as carbon, oxygen, silicon, and iron would never form through stellar fusion. Rocky planets would not exist. Neither would liquid water, stable atmospheres, or living organisms capable of wondering why the universe looks the way it does. Other constants show similar sensitivity. If gravity were slightly stronger, stars would burn through their fuel rapidly and collapse violently. If slightly weaker, nuclear fusion inside stars might never ignite. The strong nuclear force, which binds atomic nuclei together, also exists within a narrow range compatible with chemistry. This observation leads to what physicists call the anthropic principle. In its simplest form, it states that any universe observed by conscious beings must contain conditions compatible with conscious beings. At first, this sounds circular, but the idea becomes more significant once inflation enters the picture. If cosmic inflation created enormous numbers of disconnected regions beyond our horizon, each potentially with slightly different physical constants, then most regions may remain sterile forever. No structure forms there. Some hypothetical universes may expand too fast. Others may collapse almost instantly. In some, atoms cannot hold together. In others, stars never ignite. Those regions would still physically exist, but nobody inside them would ever evolve to measure or describe them. We therefore find ourselves in a functioning region because only functioning regions produce observers at all. This does not necessarily imply intention or design. Instead, it reframes the question itself. Rather than asking why the universe was built for life, physics may instead ask how many universes fail to produce life entirely. And if the broader cosmos beyond our horizon truly contains an immense landscape of regions shaped by inflation, then our observable universe may represent only one successful configuration among countless silent ones. The strange consequence is that our existence filters reality before we even begin observing it. The very act of asking why the universe permits life already guarantees we inhabit one of the rare places where the question could ever be asked. There is a point where observation ends, not because our instruments fail, not because our mathematics becomes careless, but because the structure of the universe itself places boundaries around what information can ever reach us. The cosmic horizon is one of those boundaries. Anything beyond it remains permanently disconnected from Earth by the expansion of space. No future telescope, no detector, no spacecraft, no civilization, regardless of technological power, can retrieve direct information from regions whose light will never arrive. Some limits are practical. This one is fundamental. For centuries, science advanced by extending the range of observation. Better lenses revealed moons around Jupiter. Larger telescopes uncovered distant galaxies. Particle accelerators exposed deeper layers of matter. Each generation pushed the frontier farther outward. But now we face a different kind of edge. Whether the universe extends infinitely beyond our horizon may never be known with certainty. A finite universe large enough would appear effectively infinite from inside our limited observational bubble. Measurements alone cannot fully distinguish between the two possibilities. The same problem appears again with inflation. Modern inflationary theory suggests vast regions beyond our horizon may possess different configurations of matter or even different physical constants, yet those regions cannot be sampled directly. We infer them mathematically because they emerge naturally from equations that successfully explain the observable universe. Science therefore enters unfamiliar territory, not speculation detached from evidence, but explanation extending beyond direct verification. Some physicists remain uncomfortable with this transition. Others argue it is unavoidable once observation itself encounters permanent limits. The physicist David Deutsch offered one influential defense of this approach. He argued that scientific explanations are not validated only by direct visibility, but by explanatory power. If an unseen process consistently provides the simplest and most coherent explanation for observable phenomena, then it can remain scientifically meaningful even when direct access is impossible. Atoms once occupied this category. So did black holes. For long periods, both existed first as theoretical necessities before evidence caught up. But the regions beyond our horizon may differ in one crucial respect. Evidence may never catch up at all. That possibility changes the emotional texture of cosmology. We are accustomed to believing every mystery eventually yields to investigation. Yet the observable universe may contain built in restrictions, limits woven into spacetime before the first stars formed. Some questions may therefore remain permanently suspended between mathematics and philosophy. Are there observers beyond our horizon? Does space continue forever? Do other regions obey different laws? We can construct models. We can test indirect consequences. We can narrow possibilities. But complete confirmation may remain inaccessible forever. And strangely, this is not a weakness of science. It is evidence that science has carried us all the way to the edge of what observation allows. The boundary is not human ignorance alone. It is part of reality itself, written into the geometry of the expanding universe long before we arrived to measure it. In December of 1972, the crew of Apollo 17 turned their camera back toward Earth from roughly 29,000 kilometers away. The photograph they captured, later called the Blue Marble, showed no borders, no nations, no visible history, only clouds, oceans, ice, and one thin atmosphere suspended against darkness. Astronauts who witness Earth this way often describe a psychological shift afterward, the overview effect, a sudden realization that the divisions dominating life on the surface become strangely fragile from orbit. From far enough away, the planet appears unified, finite, and delicate all at once. Many astronauts returned, speaking less about exploration and more about interconnectedness. But even low Earth orbit remains unimaginably close to home. Cosmology pushes the same perspective much farther. As we moved outward through the observable universe, the scale expanded beyond ordinary language. We passed galaxies, clusters, filaments, voids, and the ancient light of the cosmic microwave background itself. Eventually, even the observable universe, once vast beyond comprehension, became only one visible region inside something potentially far larger, perhaps infinitely larger. Inside this cosmic bubble exists every event in human history, every civilization, every migration, every library, every argument, every scientific discovery, every extinct species, every parent and child, every memory anyone has ever carried through a lifetime. All of it unfolds inside one region approximately 93 billion light years across. And that region may be only one among countless others generated by inflation long before the first stars formed. Some of those regions may contain galaxies entirely unlike ours. Others may remain dark forever. Many may contain no observers at all. But here, something unusual happened. Matter organized itself into chemistry. Chemistry became biology. Biology became nervous systems capable of memory, prediction, language, mathematics, and reflection. Through a chain of events stretching across billions of years, part of the universe gained the ability to examine the universe itself. Carl Sagan once described Earth as a pale blue dot suspended in a sunbeam. Cosmology extends that image outward another level. The entire observable universe may itself resemble a tiny, illuminated patch inside a reality too large for direct comprehension. Yet, the scale does not erase meaning. If anything, it sharpens it. Nothing beyond our horizon appears aware of us. No distant region sends confirmation that consciousness exists elsewhere. The hidden universe may contain countless observers, or none at all. We do not know. But within this visible sphere, on one ordinary planet orbiting one ordinary star, the universe produced beings capable of asking where the horizon came from and what lies beyond it. That may be the rarest phenomenon we have encountered so far. Not galaxies, not black holes, not inflation, awareness itself. For most of cosmic history, there were no observers. The early universe spent hundreds of millions of years in darkness before the first stars ignited. Galaxies had not yet assembled. Heavy elements did not yet exist. No planets circled stable suns. The universe expanded in silence, carrying only radiation, hydrogen, and time forward into deeper complexity. Then conditions changed. Stars formed, galaxies merged, supernovae scattered carbon, oxygen, iron, and calcium across interstellar space. Around at least some stars, rocky worlds condensed from those materials. On one of those worlds, chemistry crossed into biology, and biology eventually learned to ask questions about the sky. But this moment is temporary. Right now, the universe remains transparent to investigation. Distant galaxies are still visible through telescopes. The cosmic microwave background still surrounds us as faint microwave radiation. Redshift still records the expansion of space. Black holes continue merging loudly enough for gravitational wave detectors to hear them across billions of light years. The evidence still exists. That will not always be true. In roughly 1 trillion years, most stars will have exhausted their fuel. Long before then, galaxies beyond the local group will disappear permanently behind the cosmic horizon. The microwave background will stretch into wavelengths too enormous to detect. Future observers may inherit a universe stripped of its history. Imagine discovering cosmology then. You would see only one isolated galaxy surrounded by darkness, no evidence of expansion, no visible relic radiation from the Big Bang, no distant clusters, no cosmic web. The universe would appear static, eternal, and small. The true scale of reality would remain hidden. But we arrived during a narrow observational window. The universe is old enough for conscious life to emerge, yet still young enough to preserve the clues explaining where it came from. For a brief period between primordial chaos and cosmic isolation, the sky remains readable. That timing is extraordinary, and within that window, one species on one planet developed mathematics capable of describing curved spacetime, instruments sensitive enough to detect ancient photons, and theories powerful enough to reconstruct events occurring fractions of a second after the Big Bang. We measured the age of the universe. We mapped invisible dark matter through gravity. We detected gravitational waves predicted a century earlier. We identified the horizon itself, a boundary no human being can ever physically reach. But we found it anyway. The observable universe is therefore more than a physical limit. It is a temporary archive, illuminated briefly before expansion, carries much of its information away forever. Every galaxy catalogued, every background, fluctuation mapped, every distant spectrum measured represents data future civilizations may never possess. We will never cross beyond the horizon. Yet for a short time in cosmic history, the universe allowed us to see its edge, calculate its age, and recognize that beyond the visible darkness, Reality almost certainly continues far farther than any human mind can truly imagine. Long before telescopes, humanity imagined the cosmos as something arranged around us. The stars appeared fixed above Earth. The sun seemed to circle our world. Ancient maps placed human life near the center of existence because nothing in ordinary experience suggested otherwise. The sky looked intimate then, almost local, a ceiling of lights suspended over familiar ground. Science changed that picture gradually. Earth became one planet among several. The sun became one star among billions inside the Milky Way. The Milky Way itself became one galaxy drifting through a larger cosmic structure filled with clusters, filaments, and voids extending across unimaginable distances. Now the horizon pushes the idea further still. The observable universe, once thought to contain everything, may itself represent only one visible region inside a reality vastly larger than anything we can directly examine. Beyond our cosmic boundary lie more galaxies, more stars, and likely more planets than exist within all the space we can currently see, possibly without end. If life emerges naturally from chemistry often enough, then consciousness may exist throughout regions permanently disconnected from us by expansion. Entire civilizations may rise and disappear in distant cosmic bubbles without ever learning that others existed elsewhere. Not because communication failed, because geometry itself prevents contact. The loneliness implied by the cosmic horizon, therefore, differs from ordinary isolation. It is not political, cultural, or technological. It is built into spacetime from the beginning. Inflation separated regions faster than light could bridge them, and dark energy continues widening the gaps. But the same process that isolates us also explains us. The atoms in your body formed inside stars created by gravitational collapse. Those stars formed from density fluctuations seeded during inflation itself. Tiny quantum irregularities in the infant universe stretched outward across cosmic scales, eventually becoming galaxies, clusters, and planets, including this one. In that sense, the horizon is not merely surrounding us, it participated in creating us. The same expansion that carried most of the universe permanently out of reach also generated the structure necessary for observers to evolve anywhere at all. We are products of the process we are attempting to study, and perhaps that is why cosmology feels different from other sciences. When we examine the observable universe, we are not studying something detached from us. We are examining the larger system that produced every memory, language, tool, and thought we have ever possessed. There is something deeply strange about a universe large enough to conceal most of itself forever, while simultaneously generating, within one small galaxy, beings capable of recognizing the concealment, not conquering it, not escaping it, simply noticing. Across billions of years, matter organized into awareness long enough to understand that the visible cosmos is not the whole story. The horizon remains closed to us. But within this brief era of stars and detectable light, the universe became conscious enough to recognize its own hidden depths. At the edge of the observable universe, there is no wall, no barrier of stone or fire, no final curtain suspended through space. If you could somehow travel toward the horizon forever, galaxies would continue surrounding you, and your own observable universe would move with you like a shifting sphere of light. The boundary was never physical. It was temporal from the beginning. The cosmic horizon exists because light travels at a finite speed through an expanding universe with a finite age. Everything we have explored across cosmology, from inflation to dark energy to the microwave background itself, ultimately converges on this one realization. Reality extends beyond what observation can ever retrieve. And still, we found the limit. Over centuries, human beings transformed scattered points of light into measurable structure. We learned the age of the universe. We detected expansion through redshift. We reconstructed the conditions of the early cosmos from faint microwave radiation reaching Earth after 13 billion years of travel. We even identified the approximate radius of the visible universe itself, roughly 46.5 billion light years in every direction. That achievement remains extraordinary. A species confined to one planet around one ordinary star discovered that most of reality lies permanently outside its view. Few scientific conclusions are simultaneously so humbling and so profound. The horizon does not represent failure. It represents the point where physics itself closes the curtain. Beyond it, space almost certainly continues. If the universe is infinite, then the darkness beyond our observable bubble contains more galaxies than we could ever count, more planets than language can comfortably describe, and perhaps other observers shaped by the same chemistry and physical laws that shaped us. Somewhere beyond the unreachable distance, under another night sky, another civilization may have mapped its own cosmic background radiation. They may have calculated their own horizon and realized, just as we did, that most of existence remains hidden forever. But no message will pass between us. Not because intelligence failed, because space-time itself forbids the exchange. The horizon, therefore, becomes more than a cosmological concept. It becomes part of the human condition. We exist inside a finite sphere of accessible knowledge, surrounded by a reality that almost certainly exceeds it in every direction. Yet the response to that realization has never been surrender. We continue building telescopes. We continue refining equations. We continue listening for gravitational waves crossing ancient space. Curiosity persists, even when complete answers do not. Perhaps that is the final meaning of the observable universe. Not that reality hides from us, but that consciousness emerged, capable of recognizing the hiddenness at all. For a brief interval between the birth of stars and the fading of cosmic light, the universe produced observers who could stand at the edge of the known and understand there was something beyond it. And despite the silence beyond the horizon, despite the permanent distance, despite the certainty that much of reality will remain unreachable forever, we continue looking outward into the dark, asking what else might be there.